Okay, let's get started. Today we're going to be talking about variational inference again. And the goal for today is really to try to move through the rest of this picture of sort of pure variational inference, where what we're trying to do is just infer a distribution over some latent variables, right? So what we'll do later, sometime after this lecture, is we'll kind of come back to this broad idea of variational inference and think about how it can be applied to learning in a Bayesian setting. We sort of already did this with Markov chain Monte Carlo methods, where we're using an actual inference method, not to sort of find a single point estimate of our parameters, but an actual distribution of our parameters. And then we'll also think about variational autoencoders, which are sort of a method of sort of degenerative model that relies on variational inference. And specifically in that context, we'll be thinking about how we can use variational inference within the context of an EM-like algorithm, an expectation maximization algorithm. And so variational autoencoders will actually sit as sort of an example of that framework. So that's kind of where we're going here. And so what we want to do is pick up where we left off last time in thinking about how to sort of build out this algorithm in some more detail. So I guess I also just wanted to mention the usual reminders, and one that I don't have up here is I just sent out this note on Piazza about getting cloud credits for the 10.6.18 projects, and basically we can give you these kind of like coupons in $50 increments. And so if you're interested in using GPUs or sort of cloud CPUs for your project, that's an easy way to do it. There's also Google Colab, which is useful if particularly like at this point of the project where you're just trying to get things up and running, and you can actually just have access to one GPU at a time, if that's at all helpful. So kind of two different ways that you can look into that. So check out the Piazza post. The main reason I raised that is just that just sort of arbitrarily I said that the deadline for submitting the first wave of coupon requests is this Friday. So definitely fill out our Google form if you want to request one in the near term. Okay, so we said that variational inference is fundamentally about estimating the posterior, some P of Z given X, and we thought about different problem settings in which this comes up. And we said that our solution was going to be to approximate that posterior with some simpler distribution, Q of Z. And the Q of Z distribution should come from some variational family, capital Q. And what we're doing is parameterizing Q by some theta and P by some alpha. And at this moment, we're concerned with purely the setting where we want to learn the parameters theta that give us back a good approximation to some fixed P alpha. So we're assuming that you've already learned the parameters alpha at this moment. Okay, we'll come back and we'll see how we can use variational methods to also estimate alpha, but for now we're assuming they're fixed. Okay. And what we want to focus on today is really this mean field approximation algorithm. And so last time we saw these examples of how you could actually take, say, a Markov random field like this one and decompose it using a mean field approximation, where we say that basically there's no connecting edges in our graphical model. And so the next thing that we actually need to do is identify a little bit more about the actual objective function that we're going to be working with. So the objective that we want to use here is that of KL divergence. And so we're assuming that we've decomposed Q as the product of a bunch of sort of little Q distributions. And I guess one thing I'm just noticing here is in my definition of the mean field assumption at the very top here, I kind of lost track of theta. So we could say, maybe put theta inside the parentheses. So it's also parameters to the QT distribution. I guess we could have subscripted it alongside the little t, but maybe we're just kind of running out of space there. So we're going to try to pick the Q that minimizes KL divergence, and then optimize with something like coordinate descent. Okay. So the next thing that we want to think about here is the mean field objective function. And the first thing that we should note here is that really, so the question that we're asking is, how to optimize this KL divergence objective. And essentially we're saying that, our original optimization problem was that we want to find some parameters alpha or some distribution Q that minimize the KL of Q alpha of Z and other way around. So we want to find some theta that minimizes Q theta of Z and P alpha of Z given X. Okay, so the problem is this KL term we can't actually compute. So specifically, we said that, so let's see why here. So we defined the KL divergence just sort of generally for two distributions. So here, let's just write it out for this Q of Z and this P of Z given X. So its form is going to be the expected log of a ratio, where the expectation is taken under Q of Z of the log of Q of Z over P of Z given X. And so at this moment, we now want to divide up this expectation into two terms so that we have the expectation of the log of Q of Z minus the expectation, again under Q of Z, of the log of P of Z given X. So why can we do that? Well, this is just the log of a ratio. The log of the ratio is just the log of the numerator minus the log of the denominator. And so by linearity of expectation, we can just take the expectation of the log of numerator, expectation of log denominator. Okay, so far just some simple manipulation. And then we can observe that, P of z given x is really P of x and z divided by P of x. So that means that really what we have here are more terms where we can take this second term and break it up into a log of P of x and z minus a log of P of x. Okay, so that would look like P of q of z of the log of P of x. What is the expectation under q of z of log of P of x? Can anyone simplify that for me?
It's just log of P of x.
It's just log P of x, right? Because if you have some random variable, right, and you're taking an expectation under some distribution over that random variable of a constant, then the expectation is just the value of the constant. So this might be like 27, or sorry, it's a log probability, negative 27. And so this expectation is just whatever that value is, negative 27. So what we're left with is the difference of these two expectations minus log P of x. Okay, and much earlier on here, we actually assumed this was intractable. That was how we kind of walked into this whole thing. So we said from the get-go that this term was something that we couldn't compute by assumption. Okay, so if we can't compute that term, then we can't compute the KL divergence. Okay, so what are we going to do? Well, let's think of some alternate objective function that we could actually work with instead. So if we say now that, what it is we're trying to do is, here actually, maybe I'll actually switch to, we're going to be really sort of focused on the behaviors of the distributions here. So essentially what I want you to be comfortable with is sort of what we were doing before, which was to say that, we can talk about this optimization problem in one of two ways. We can talk about it as an optimization problem over parameters theta, or we could talk about it as an optimization problem over the variational family. These are just two ways of talking about the same problem, right? Either way, we're getting back some Q distribution. It's just a question of whether we talk about it as optimization over parameters or optimization over the distribution. Okay. So I think we'll stick with the way that I set it up here, which is optimization over parameters. And I think it's just sort of a more natural way to actually talk about this stuff. That said, as we're jotting down notes here, we're purposefully going to leave out the parameters for most of the time just because we don't want our hands to like cramp up while we're writing all this. So, okay, so what we want to do next is we want to say that finding this theta, which is the argmin over KL Q theta P alpha. Okay. Well, that is equal to the argmin over these three terms that we just wrote down, right? Expectation under Q theta of the log of Q theta actually I should be careful here. So this second term, I actually sort of made a mistake on the sign here. So the first term, the expectation of log p of z given x was subtracted. So when we divided out the numerator and then moved it out, this really should have been a plus. On those last two terms. Okay, so this p of x is a function of alpha as well. It's just that we're marginalizing over z. Okay, so this is minimization over theta. And we can't compute log p alpha of x. So what should we, oh yeah, question.
Should be z and x, z and x.
Oh yeah, thank you. Yeah, x and z. Good catch. So, all right, so we can't solve this optimization problem. So what should we do?
I have a question.
Yeah.
So when we say that P is characterized by alpha, are we saying that we know the function form of P? Or
Yeah, so we
how
know,
do we,
sorry, what's
how
that?
do we know that?
Oh, we chose it. I mean, this is the distribution that you came up with, right? If you were doing Markov chain Monte Carlo, this is the distribution, right? This is the thing that came from, I don't know, say the graphical model that you're working with, right? So P alpha is, the actual, complicated distribution that you care about. So maybe here we have something like, P alpha of z given x is something like, we have z1 and z2 and z3, and all of these things are kind of connected up to some x's that we observe, x1, x2 in interesting ways, like so. And we could say, so a little clearer. So these x's are shaded in because they're observed. And then what we're saying is that separately, we might have some q theta of z that just has the same support. So it also has variables z1, z2, and z3. But maybe they're under a mean field assumption. And so they just look like this, with little factors touching each one. So that's the setting that we're in, and we're assuming that you know all the factors involved in P alpha. So you can compute. Okay. So the question here is we want to minimize over theta this KL divergence, but we can't compute log P of x, so what should we do?
Could be more because it doesn't depend on theta.
Yeah, great idea. Log P alpha of x isn't a function of theta. If we're just minimizing over theta, let's just ignore log P alpha of x, right? So we could even say, we're just gonna take an argmin over theta of just the first two terms. So that would be this one and that one, dropping log P alpha of x. Now, this is such a good idea that we're going to give this idea a name, but we're not going to give the first two terms a name. I'm actually going to negate them and then give them a name. So if I negate them, then that means that we're going to be now doing an argmax here, not an argmin. and we're gonna do some objective function called the ELBO, which is a function of q theta. Okay. So the ELBO, let's just define it, of q theta is going to be defined as the negated version of those two terms, which is just the expectation under q theta of z of the log of p of x and z minus the expectation under the same q theta of z of the log of q theta of z. And if you want, we can include this alpha here, just to be big. All right, so now, I guess the remaining question is, well, we got rid of this one term that we knew we could compute, but what about those other terms? Are we even going to be able to compute them? Are we going to be able to actually do learning with them? So it turns out we will, and we'll be able to precisely because we've chosen q theta of x to have a really simple form. Okay, and we'll see how that plays in here in just a moment. So I guess another thing to note here is that for a factor, so for a factor graph, we would have written things out a little bit differently, right? So for a factor graph, we would have written this as, oops, we would have said this was equal to an argmin over theta of this e of q theta log q theta minus, and then the second term would have been of the log of p tilde of x and z, or say z given x. And then we would have had not log of p of x, but the log of the partition function, z of x. So if we are in a situation where we can't compute this partition function, then we would drop that to get the ELBO. So this is just the same thing, but for a factor graph. Or rather, I guess I shouldn't say for a factor graph, I should really say for a conditional random field. Okay, so now we have this objective function. And before we actually put it to use, I want to just sort of make a few notes about this new objective function. So this is just sort of some side notes about the ELBO. So the thing that we want to highlight here is, you know, the reason that we're using the ELBO here is because it's going to get rid of that intractable term. But there's also this, well, I mean, I'll call it a theorem, but it feels a little bit funny even calling it a theorem because it's an incredibly simple statement. So for any distribution Q, the log of P of x is greater than or equal to the ELBO of that Q. So what that means is that, in other words, ELBO of Q is a lower bound on log P of X. All right, so we could actually prove this, and let's prove it two different ways. So the first way is going to use Jensen's inequality, and Jensen's inequality is just a statement about how we can work with functions of expectations. So Jensen's inequality here, it might have been something that you actually saw in your probability class. So it just says that a function of an expectation of a random variable is greater than or equal to the expectation of that function of the random variable. We could probably spend like an entire probability type lecture just talking about that inequality. I don't really want to do that here. Instead, I just want to see how we can use that inequality in our setting to show that this is indeed a lower bound. So there's really just sort of one step here. So we're going to start with the fact that the log of P of X is just the log of a marginal probability. So it's a marginal over Z of the log of P of X and Z. Oops. Where we integrate over possible values of Z. And then we could say that we're able to just take this and multiply by 1, where here 1 is defined as Q over Z divided by Q over Z. Okay, so this was really just multiplying by 1. And then we can actually now look at this as an expectation. Namely, we can call this an expectation under Q of Z. So what we're going to do is we're going to take this numerator, Q of Z, and move it out to the front. So really this, we could say, is just an expectation of under Q of Z of P of X and Z divided by Q of Z. Right. So this is just definition of expectation. So we got that by sort of moving this Q of Z out to the front. And then at this point, our next step should hopefully be straightforward. Does anyone see what it is?
Should we bring out the expectation?
Yeah, just apply Jensen's inequality, where f is just a log function, right? So what we get is that this must be greater than or equal to the expectation under Q of Z of the log of that ratio. So that's by Jensen's inequality. And okay, lastly, by just strict equality, we have that that's equal to, and now I'm just going to divide up those terms as we've been doing, the log of P of X and Z minus the expectation of the log of Q of Z. Okay. Great. So that is just the ELBO of Q. So that proves what we were setting out to do, which is that the log of p of x is greater than or equal to ELBO of q. Okay. So it turns out that what we just did here was a whole bunch of work for nothing. Here's proof number 2. Okay. So proof number 2, you just need to know a little something about KL divergence. So, so step 1, we have that the log of p of x is equal to the KL of QP plus the ELBO of Q. Okay, so does anyone want to give me just why is this the case? Why is it that the sum of KLPQ plus ELBO of Q is log P of x?
You should just write the equation together on p of x with
Yeah, the two terms are just going to cancel out. The whole point is that we negated ELBO. We negated the first two terms of the KL, and that was the ELBO. So we're just, by adding the two, we're just getting those to cancel out. Okay, so this is just sort of by our very definitions of the ELBO. Okay, so so how can we show very directly that the sum of, well, that given this statement, that ELBO is a lower bound for log of P of Q? Give you a hint, it requires a property of the KL divergence.
Is it always positive?
Yeah, so KL of QP is greater than or equal to 0. Actually, is it greater than or equal to, or is it greater than? I guess
Equal to.
it could be equal to 0 because we could have all of the Q terms that are 0 probability be where P is non-zero, vice versa. Okay, so it's greater than or equal to 0, which means that log P of x is greater than or equal to ELBO of Q. Okay, so so really, everything that we just did in proof 1, this is just sort of the standard way of proving KL is greater than or equal to 0, or similar to. So if you wanted to prove this fact, you would use Jensen's inequality, okay? And we just did it directly on log P of x. Okay, so why are we belaboring this point? Like, what is the takeaway message here? So the takeaway is that in variational inference, we are finding the Q that gives us the tightest bound on the marginal data likelihood. So, in a sense, oops, sorry about that. We just find the Q that gives us the tightest bound on the marginal data likelihood. And so what that means is that essentially we're trying to make the actual observed data, x, as likely as possible under this Q distribution. You can think of it, that is effectively what we're doing. So this statement is actually going to become more important once we come back and try to learn both the parameters theta of Q and also the parameters alpha of P. Because what we're going to do when we come back to this later and we want to learn the parameters alpha of P is we're going to look back at this ELBO definition here. And we're gonna say, well, really, ELBO is a function both of the parameters theta and also the parameters alpha. So let's tune jointly the parameters of theta and alpha to maximize the ELBO. And maximizing the ELBO is essentially trying to maximize the marginal data likelihood. So we'll come back and we'll do that later. So if that's not obvious, don't worry about it just yet. Okay, so now we've sort of laid out this whole ELBO thing. And I guess maybe the most important detail I left out here is just that, so why do we call this thing ELBO? ELBO stands for evidence lower bound. So evidence lower bound, where we take the B and the O from bound. And now we've actually seen, it's a lower bound on the evidence, where the evidence is X, the actual observed data. All right. So from here, we want to say, let's actually solve the problem that we set out to solve. And the first way that I want to sort of allude to solving it, and we're not actually going to go through this fully, is to use gradient descent. And the reason we're not going to fully go through this version is we're going to sort of leave this, Akanksha, could you make a note about this? We're going to leave mean field with gradient descent as sort of an exercise in homework 5. And so what we'll do is we'll sketch this out, but we'll leave sort of the last step of deriving some gradients open-ended. And then what we'll do is we'll come back and we'll actually look at those gradients, but from a slightly different perspective, and we'll do coordinate ascent. Okay, so I want to start here because we all know gradient descent really well. This is sort of where it feels like we should start if we're just trying to optimize this objective function. Okay, so suppose we want to find this theta hat that is at least approximately the argmax over theta of ELBO of q theta. Okay, so that's the setup. Gradient descent does local, I guess we need not gradient descent, but gradient ascent here. So gradient ascent does local maximization. Okay. But the ELBO is generally non-convex. Okay. So whatever solution we come up with here, we're not going to actually try to deal with that non-convexity. We're just going to do the usual thing and rely on local maximization algorithms, just for simplicity. Okay, so then the whole point is let's apply gradient ascent to the ELBO. Okay, so what would that look like? Well, the algorithm is just going to be pretty simple. We're going to say in step 1, initialize your parameters theta. And then in step 2 of the algorithm, we'll say, while we have not converged, or while we're waiting for some convergence criteria to be met, we're just going to update the parameters theta with the usual gradient ascent update, which is going to be theta, not minus, but plus here, because we're doing ascent. Some learning rate gamma times the gradient with respect to theta of ELBO q theta. This is a learning rate. Okay. So now all we need to do is come up with the gradient of the ELBO. So roughly, that's going to look like we have the gradient of the ELBO of q theta is just the gradient of two terms, namely the expectation under q of z, or q theta of z, of the log of p alpha of z given x. Right? So that's the first term, minus the gradient of the second term, which is just the entropy of q here. So expectation of the log of q theta of z. Okay, so figuring out exactly what those gradients are is a nice little problem for homework 5. And the detail here is just that but this is easy precisely because of a simple q function. So this is our this is sort of one version of mean field, right? Where we would just run gradient descent as long as you can compute those gradients. Okay. So at the end of this, right, you'll have run gradient descent, you'll have come up with some theta hat, and the whole idea is use q hat, or whatever, q theta hat, I guess, of z as an approximation for whatever distribution you're approximating. So, namely, observe that q hat of z, we chose it to decompose over the variables. And so what that means for us is that, we can actually, this is our approximation to p alpha of z given x. So there's sort of like two things that are really important to observe here. So two cases to consider. Suppose the one thing you wanted to consider was computation of variable marginals. Okay, so if you think about running the belief propagation algorithm, the two things that you walk away with are variable beliefs and factor beliefs, right? So here, why was it that we wanted variable and factor beliefs? Well, you could use variable and factor beliefs to compute an objective function like the log likelihood for your model. Okay, so one thing we might want are variable marginals, such as p alpha of zt, right? Which is exactly, defined as a sum over all sort of variables in the vector z not t of the joint of zt and z not t given x. Oops, I guess we could incorporate our x here into the variable marginal as well, since really right here we have this variable marginal conditioned on x. And what we're saying is that if we have this q function, then this is trivially approximated by qt zt given theta hat. Let me write this actually a slightly different way, because really what we're saying here is that what you get back for this qt-zt, this is approximately equal to the variable marginal that you care about. So, yeah, so the point is that the way that you would approximate this is using that qt. Okay, so what if you wanted something like factor marginals? I'm going to put that in quotes here. Well, then in that case, you want to approximate that with, say, qt of, say you had some variables like zt and zs. So this is just going to be an example of a factor marginal here. So this would be, this is just an example for two variables. So if we wanted to have that, we could say that that is approximately equal to p alpha of zt zs given x. So the question is, how do we actually compute this marginal? Like, how do we actually get qt of zt and zs given theta hat? What is that equal to? Is it easy to compute? Is it hard to compute? All right, why don't we step through it? So what is the definition of this marginal of multiple variables? How about to make this even clearer? Oh, sorry. I guess I shouldn't have used a t in the subscript here. This would be like, it's a q of these two variables. It's not just t, it's of both. So maybe just so that we can actually see what's going on here, what if I said we want q of z1 and z2, marginalizing over all of the other variables? So how do I even define this marginal probability? Yeah.
It's like the sum of like, just marginalize out all the other variables.
Yeah, so like we'd have a sum over all the values of z3 and a sum over all the values of z4 all the way out to say z capital T. And what would we be adding up? We'd be adding up the joint, which is just q of z1, z2, all the way up to zt. Okay, so how how did we define that joint distribution? Well, we defined the joint distribution to decompose as the product of, from t equals 1 up to capital T, of q of zt. Or written another way, I mean, this product is really like q of z1 times q of z2 all the way up to q of z capital T. So that means that we can rearrange terms by pushing these down through these summations. So this should actually feel kind of like what we were doing in variable elimination, right? We have q of z1 times q of z2 times a summation over z3, q of z3, summation over z4, q of z4, right? All the way up to a summation over zt, q of zt. Okay. So what is this term? One. What is this term? One. This entire thing. One. Okay. You can just work your way back. Since each one of these little summations is going to be 1, then this one was 1, and then the one before it, also 1, and also 1, and also 1, all the way back. And so that means that this marginal just boils down to q of z1 times q of z2. So more generally, we have that these factor marginals are just going to be q of zt times q of zs. And this whole thing, so maybe I should say, these aren't really factor marginals because we don't even have any factors in the q factor graph. These are, say, 2 variable marginals. Okay. And then we can just kind of keep going, right? 3 variable marginals, if you want them, are just q of zt, zs, zr is equal to q of zt times q of zs times q of zr. And so on for more variables. Sorry. Okay, so this is why we worked with a distribution like Q. Because once you boil down to a mean field approximation, all of the things that are usually really tricky become really easy in Q. All right. So, so now I want to look at one more variant of actually doing mean field here. Oh yeah.
Is the assumption that we make in mean field similar to the assumption that we make in 90 days, that everything is independent?
Yeah, I guess the point here is that everything is conditionally independent given the parameters theta. So all of those, so I could even say sort of that the, conditional independence properties of mean field, I mean, they all boil down to a little Bayes net that looks like Z1, Z2, ZT. Right. So once you actually observe theta, they're all independent of each other. So the way that I've been writing it down is instead as a factor graph, like Z1, Z2, and ZT, each with these little factors. But it amounts to the same statement where here I'm just not actually visualizing theta as a random variable, I'm visualizing it as, fixed parameters of the model. Yeah.
So would it be right to say that as the complexity of Q approaches that of P, the lower bound will be tighter?
Yes. Yeah. And in fact, just to take a little bit of, say, a stretching break from all of this math, why don't we actually think about kind of an interesting case, and then we'll come back to coordinate descent. So, what if we were to talk about map inference as mean field, or as variational inference, rather? So suppose we wanted to cast the map inference problem as a variational inference problem. So we want a family Q such that Q of Z, which is the argmin of all possible Q's in capital Q of KL QP, gives back a distribution which is a point mass. Where Q hat of Z is Z hat equal to the argmax of E of Z given X with probability 1 and anything else with probability 0. Then the question is, in this case, what is Q? So if Q is equal to P, then when we solve that KL, we just get back P. But here we're trying to actually do something kind of wacky. We're saying, I actually want to solve the map inference problem. The map inference problem, remember what it does. I mean, I wrote it in here. The map inference problem is saying, so the map inference problem just says we want to find Z hat, which is the argmax over all possible Z's of P of Z given X. It's just finding the most probable assignment to the variables under P. Okay, so what essentially I'm driving towards here is, what if we defined Q so that it was just the family of distributions where each distribution was a point mass on a different z.
So the Q, like, Q of Z attribute.
So we could, yeah, so basically what we're saying is each member of Q, some Q in Q, is a point mass for some z in the space of all possible z's. So that means that we're playing a little bit of gymnastics here, right? We're saying Q is always going to be, like you could think of it like, this is sort of a wacky notation here, but Q of Z prime of Z is equal to 1 if Z prime equals Z and 0 otherwise. So in this way, what we're saying is we would have this, this funny little collection of distributions where each one just gives probability to one particular assignment. So if you have a distribution that gives probability to only one assignment, the one that minimizes KL divergence is going to be the one with highest likelihood under P of Z given X. And so in that case, that would be the Q hat that we came up with here. Okay, so finally now let's return to this mean field problem. And let's look at one more way of doing things. And this time we're going to look at coordinate ascent. So coordinate ascent is just, so if you recall the coordinate descent algorithm, it just alternately optimizes along each dimension. So if we had some function that we were trying to optimize, and it was a function of x1 and x2, and the function was something like this, j of x1, x2. We would pick some initial point, and then starting at that initial point, we would step along the x1 axis to the highest value of x1, and then we would step along the x2 axis to, say the highest value of x2, and then along the x1 axis. And so all we're doing is just sort of going back and forth between x1 and x2. So the k-means algorithm is block coordinate descent on cluster centers and cluster assignments, right? We do this alternating back and forth between updating cluster centers and updating cluster assignments. The expectation maximization algorithm is also a block coordinate ascent algorithm where we have a block of variables. So here we're actually going to do coordinate ascent, meaning one variable at a time. Okay. So the algorithm here is called coordinate ascent variational inference, usually abbreviated CAVI. And in CAVI, we're going to say, while the ELBO of Q theta has not converged, we're going to iterate through each of our variables. So let's say for t in 1 up to capital T, we're going to set qt of zt to be equal to, or rather proportional to, the following quantity. So it's going to be, and we'll come up with how we actually get this in just a moment. It's going to be the exp of an expectation, where the expectation here is taken with respect to all of the variables except for t. So let's call that distribution q of not t. And the expectation is going to be of a conditional, a log conditional probability that looks just like the log full conditional that we worked with in Gibbs sampling, namely the probability of zt given z not t and x. Okay. And then we can compute the ELBO of our current Q, and then at the end, return Q. So the way to sort of conceptualize what's going on here is that in Gibbs sampling, so like Gibbs sampling, we compute sort of a variable specific quantity at each step, conditioned on really the Markov blanket. All right. So unlike Gibbs sampling, we compute an entire distribution that's instead of sampling a value. And we condition on variable marginals, those Q distributions, instead of on an assignment to those variables. So you could think of this as, we're going through each variable at a time, recomputing the distribution for that variable. And then we're using the expected log conditional to recompute that, which is sort of like, what we expect, or what all of the other variables expect that distribution to be. So another analogy that we can draw here is, so this is similar to belief propagations message passing. How is it similar? Well, we update our variable belief based on what neighboring variables think it should be. So, you know, the neighboring variables have some belief about what the distribution over this QZT should be. And we're updating that belief based on their understanding of what that distribution should look like. And we cycle through variables one at a time to do that. Okay. So,
If in mean field everything is, all of the variables are independent, right? But if there was something like only two of them are joint like that, would all of these three conditions hold? The similarity that we are drawing.
so if in mean field we didn't have, are you saying if we didn't make the mean field assumption that there was one
Yeah.
factor per variable? So yes, and actually let's, in favor of, so the thing that we're going to do next is derive this update, okay? Which is going to be like very closely related to the actual gradient descent version, right? I mean, at this point, you can imagine how we're going to derive that update. We're just going to compute the derivative of the ELBO with respect to this distribution, and then we'll set that equal to 0 and solve for it, so that we're maximizing that value conditioned on all the other ones. Okay, so instead of jumping into that just yet, let's actually leave off with one more connection here. So, all right. So if Q is not a mean field approximation, but decomposes over, say, blocks of variables, then we have what's called structured mean field. And we would say that this is okay, we'll just end the lecture really quickly. So which is, oh no, there I have power. Which is analogous. Huh. Uh-oh. Okay. To what's called generalized belief propagation. Which is also analogous to block Gibbs sampling. Okay, so what's ridiculous here is we have structured mean field, generalized BP, and block Gibbs sampling. And these are just sort of obnoxious adjectives chosen by different people. So essentially, the fact that these names differ, like it would be great if they were just all, you know, block mean field, block belief propagation. Block gives sampling. For whatever reason, these things kind of developed independently, and we ended up with these names that don't make this connection obvious at all. But really, that's what's going on here. It's that they're very closely connected in that way. Okay, so next time, we'll kind of get a feel for what this looks like on a tiny factor graph, and then we'll actually derive that update. And from there, we'll step into either some other variational methods or variational EM. I might actually bump up variational EM just so that we can talk about it right after this. Okay, so see you then.